Welcome to Precalculus Concept 37A, underneath additional topics in trig. This is called Vectors Part 1 of 2, and there's 4 boxes for us to talk about. So let's get right into it here. This is box 1, and box 1 wants us to use magnitude and direction to show that two vectors are equal. So before we can even get into that, we need to understand what a vector even is. So if you look at this graph over here on the left-hand side, I have 5 vectors for you. I have vector h, vector I, j, k, and l. And a vector is just a directed line segment in the plane. It's a directed line segment in the plane. The word magnitude is a fancy word for length, and the word direction is a fancy word for slope, basically, is what's going on here. What we're going to do is we're going to show that vector h, which is this one right here, and vector I, which is this one over here, but my blue and my red one, we're going to show that those are equal by showing that their magnitude and their direction are the same. Some people think that vector L is the same thing as vector I or h, but it's not, because L is pointed in the opposite direction. So let's take a moment and talk about the vector itself. So it has an initial point right here, and it has a terminal point over here. And the way that I know that is because the initial point has a little dot, and the terminal point has an arrow. So nonetheless, P or vector h and I are going in this direction. We're in the same direction as vector j, but vector j is not nearly as long as vectors I or h, so they are not equivalent. Vector L is the same length as vectors h and I, but it goes in the opposite direction, so it's not equivalent either. And then of course vector k over here is a random longer vector. So the length matters and the direction matters. So let's go ahead and show that h and I are equal. If you think about it, you can see that we visualize a triangle here. We have a right triangle, and this distance is 3 units, and that distance is 3 units. So the magnitude, which we'll just call, in this case, x for right now, would just be the Pythagorean theorem. So the let's talk about vector h. The magnitude, which is denoted by 2 vertical bars of vector h, is going to be the square root of 3 squared plus 3 squared, which of course is just the square root of 9 plus 9, which is just the square root of 18. You can leave it like that for right now. Let's take a look at I, vector I. The magnitude, again denoted by 2 vertical bars, is just going to be the square root of, well, go ahead and draw that same triangle. That's 3 units, that's 3 units. So 3 squared plus 3 squared, and you get the square root of 18. So far we can see that their magnitudes are the same. Now we just take a look at their slope, right? So the slope of vector h, so if I just do the slope of vector h, is going to be up 3 over 3. 3 over 3 has a value of 1. And then the slope of vector I is just going to be up 3 over 3, which is also 1. So because they have the same magnitude and the same direction or the same slope, that's enough to say that the two vectors are equal. Okay, box 2, we're going to visualize scalar multiplication, vector addition, and vector subtraction. So take a look in the plane. I have 3 vectors for you. I have vector v, which is over here. I have vector u, which is orange, and then have this vector w, which is green. And what we want to do is we want to visualize what does it mean to do 2 times vector v. What that means is we want to increase the magnitude by 2, or basically we want to stretch this vector out to be 2 times as long. So 2v would be the vector that looks like this. So let's start here. And instead of going over 1, 2, and up 1, I would go over 1, 2, 3, 4, and up 2. And if I drew that, this would be 2 times the length of vector v. Notice that I keep it in the same direction because I just want to double the magnitudes, double my vector's magnitude. Let's talk about negative v. Negative v is going to be the same length vector but in the opposite direction. So instead of going to the right 2 and up 1, I would go to the left 2 and down 1. So if I'd have this would be negative v. So a negative sign in front of a vector means the opposite direction but the same length. If I wanted negative 3v, I would start here, and I would draw a vector that is 3 times as long in the opposite direction, negative 3v. I just kind of eyeballed that. Half of v would be a vector that is only half as long in the same direction as v. Now let's talk about how to add 2 vectors together. Let's talk about u and w. So let me erase these really quick here for you. Let's erase this one so we can have a clean slate, and then erase this one. I'm going to show you something pretty cool. Okay. So if I'm interested in adding vectors u and w together, one way that we could do this is by the tip to tail method. So what that means is we are allowed to move a vector around the plane as long as we don't change its direction or its magnitude. So what I mean by that is, check this out, if I were to take this vector, then I can actually pick this vector up and move it in the plane and put it from tip to tail of vector u. The sum is going to be this vector right here, the resultant vector. That is the representation of u plus w. That's pretty cool. As long as you go tip to tail, we haven't changed the direction or the magnitude, the resultant vector is going to be that. Okay? So let me pause and show you a visualization of u minus w. Okay, let's talk about u minus w. So what I want to do is I want to draw negative w. So negative w is going to be, instead of going down 2 and over 2, I'm going to pick this one up. Let's draw it here. I would go left 2 and up 2. So this is negative w. So if I want to add u plus a negative w, I would then be talking about my purple and my orange vectors here. So what I would do is then I could take this one as well. I could pick it up and I can move it. I would put it on the tail or the tip of vector u, and then I would draw the resultant vector here. So this would be the sum of u plus negative w. So that's a kind of a cool visual way to see what we're doing in the plane when we move these vectors around. Okay, here's a quick little U-try in box number 3. I have given you vector v, which is this blue highlighted one over here in the bottom left-hand corner. I'm asking you which of the following vectors, either p, a, b, or w, represents 3v. Hopefully you got the right answer of vector w represents 3v because it is 3 times as long and it is in the same direction as vector v. Vector b is not, because even though it is 3 times as long, it's not in the same direction. And vector a is in the opposite direction, so even though it is 3 times as long, not in the right direction. Of course, vector p is just a totally different vector. Okay, last box here is how to represent a vector in the rectangular coordinate system. So take for a moment this blue vector, vector v. And what we're going to do is we're going to learn how to break down vector v into its components. It's going to be an x component and a y component. Although when we're talking in vector land, we talked about I and j's. So the I component is the horizontal component and the j component is the vertical component. So I could represent this vector v in terms of its components by saying it's the same thing as 6 units in the I direction plus 3 units in the j direction. So vector v could be represented as 6i plus 3j. And the cool thing about this is that it doesn't really matter where that vector is in the plane. Like for example, if I move this over here, this vector would still have the same components of 6i plus 3j. It doesn't necessarily have to be centered at the origin. All we care about is its I components and its j components, meaning how far it is left and right on the x's and how far it is up and down on the y's. We're going to use this one in the next video. Hope that makes sense to you.